Thanks, Avian, for the invitation. So this is joint work with Casper Green Larsen and Watching You. And I should probably say that, even if you don't care about data structures, this talk probably, hopefully, contains some interesting connection between information theory and algebra or functional analysis. And I just hope that I get to that part. It's going to be a race, but I'll do my best. So first of all, what is, I think the slide is cut. Okay, I'll continue anyway. So, okay. So what is a data structure first? I'm sure you all know. So essentially, a data structure is just a compact way of representing information in a database so that queries about the underlying data can be answered efficiently by accessing few memory cells. So in the simplest kind of vanilla version static data structure model, we are giving a database in advance. So let's say a road network on n vertices. It can be some n-bit string and n points in some high dimensional space. And we need to pre-process this database, which we are given in advance, so that upon a query, when a query is invoked, so in this case just a pair of cities maybe, we can compute the answer to this query very fast, very quickly. So notice that any such static problem has two naive or extreme solutions. One of them is to just cheat and store all the answers, pre-compute all the answers. Of course, the query time in this case is amazing. It's just one probe. Of course, the problem is that we need to store the entire truth table, and the number of queries is usually polynomial in the database. So here it's just n squared pairs, but this n squared can be n to the 100 usually. And that's the interesting regime where the number of queries is polynomial in the size of the database, and that's also the more realistic case. The second solution is to do nothing clever, just store the database as is, and then when we are given a query, we can run our favorite algorithm, for example, Dijkstra's shortest path algorithm. But of course, in this case, this ad hoc algorithm might require a linear scan of the full database. So the space is ideal. It's the best. You're just storing the database. You must store the information theoretic minimum regardless of the query time, or else you can't. Anything is hopeless, even with infinite query time. But the query time is slow. It's potentially linear. Okay? And of course, the question is, are there better data? Is there something in between? Can we have better trade-offs? And this is exactly the question that static data structure lower bounds try to study, the trade-off between time and space. Okay? So in the dynamic model, right, our database is not given in advance, but is rather evolving over time in an online fashion. So the goal is to maintain an online sequence of interleaved updates and queries as cheaply, as economically as possible. Right? So for example, suppose we have a growing company, and we want to maintain a database, an online database of the employees, such that we're able to add, maybe hire, maybe even fire, but in this case, hire new employees with certain salaries, and we want to support total salary expense queries. Okay, so of the form, you give me a year, and I need to return to you how much salary did the company spend until this point. So in this case, updates are just a year and a salary, and queries are just specifying a year, and you need to return the answer. So again, the naive solution for such a dynamic problem, suppose we have this online sequence of updates and queries, is just to maintain a counter for each year. Right? If we hired an employee with a salary of 4 in 2005, we just increment the counter, and then 2000, the salary of 2, and then we query how much did the company spend on employees hired before 2007. Of course, the update is cheap. It's just constant, but the query requires a linear scan again. So the query time is slow. Okay, so the update is very cheap. The query is expensive. Then you can think of maybe we can build more.
Query here only?
A query is just a year, and you need to return the sum of points.
Sum from everything before.
Yeah, yeah. So how much salary in total did we spend on all the employees? Okay, so the query time is linear in the number of years you can be hired, which is linear in n. Remember, n here is the number of operations, the length of the sequence. You can think of maybe doing something more clever, which is building a tree on top of these years that you can be hired. In this case, each update simply needs to add the salary to all the root to leaf paths leading to the correct year. And it's not hard to see that when you're invoked with a query, if you just sum up all what is hanging off to the left of the root to leaf path to the corresponding year, you'll get the correct answer. So in this case, we compromise the update time a little bit, but we have much faster, exponentially faster query time. Okay? And some of you might recognize this toy problem as the special one-dimensional case of the classic range counting problem. In the high dimensional, or let's say two-dimensional case, we're given a set of points in the two-dimensional grid, or maybe d-dimensional. The query is just a point, a rectangle, an axis parallel rectangle, and the answer is to report the sum, or maybe the weighted sum, of points inside this rectangle. And this problem goes way beyond the scope of this talk, but you cannot overestimate the importance of this problem. So, SQL and eBay solve this problem on a hourly basis. This is really, return the size of the market of all people which are between age 25 and 34 with a salary so-and-so from location, blah. So this is a really fundamental problem in spatial databases.
So updates there is adding a point.
Exactly. And maybe even, in this case, just that. Okay, so and it turns out that a generalized version of this tree called range trees solved the d-dimensional version of this problem, not in log n, but log to the power d, the dimension. So in the two-dimensional case, log squared n, roughly, updates and queries. And try to remember that this will come back future of this talk. So the goal in dynamic data structures is to study the trade-off not between space and time so much, but between the update time and the query time. And the reason is that space is essentially captured by the update time, right? If it's not a hard exercise, if the update time upon each operation is tu, then the space you use on a sequence of n operations is never more than n times tu, and n is a trivial lower bound because you just need to store something about every update. And the holy grail is, again, to answer, is there a better data structure for this? Can we enjoy both worlds? Is there something in between? And the holy grail here is to really prove an unconditional trade-off, an unconditional lower bound on the maximum, let's say, of the update or query time. So you want to say range counting has to take, either your update has to be expensive or your query. Does that make sense so far? Okay, so in order to prove such lower bounds, we need some model, right? We need a model of data structures. So, and ideally, such a model will capture any imaginable data structure. So we want our lower bounds to hold whether you program your data structure on an iPhone or in your laptop compiler, whether you're using C or Java compiling languages, or different assemblers. And this is exactly the motivation behind the CellPro model. So in the CellPro model, a data structure, a dynamic data structure in this case, is nothing else but a consecutive array of points and of integers, where each cell in the array can store W bits of information. So W is called the word size, and it's typically set to log n. And intuitively, the reason for this assumption is that log n seems a natural value, because if you have n updates, you want to be able to, for example, index an operation. This takes log n. You want to be able to store a pointer to some other cell, which is also log n. So the address space is 2 to the w, roughly. All right, and this is an important feature of the model. So in one operation, you can access an entire word. So the operations, the granularity, the atomic granularity is the word size.
Omri, N is fixed once and for all at the beginning.
Yeah, n is a parameter denoting the length of the sequence. Yeah.
So I know beforehand how many updates and
Sure.
I'm going to
But
get.
even if you don't, it's usually the standard doubling thing. You assume
Yeah.
it's going to be
Yeah.
100, then you assume it will be 200, then it's geometric. So you can
Yes.
assume,
Yeah. For example, I think in the streaming community, you don't typically assume length of the sequence. But for this talk, the n is just the.
and it was invented before the cell phone.
Really? Okay. Good to know. That's true. Okay, so what is a CellPro model? So let me not save you the formal definition. So we're given a sequence of updates. The data structure, upon an update, it's going to perform some maintenance operation to reflect this update, right? And can do arbitrary things. So maybe it reads the third cell and writes some content to it. And again, on the second operation, it might probe the fifth cell, write something, and then said, oh, I want to override the content of this cell and write something else. And in general, we have a long sequence of updates. And then upon a query, okay, so I should say the update time is just the number of cells that you touch, that you probe on this cell, okay, either read or write. Okay, what you choose to do with those cells, you can solve NP-complete problems. We don't care. All we care about is how many cells you touch and probe. Okay? Upon a query, the same story. So now we have we're prompted with a query. The query is going to probe, or it's going to read some number of cells, at most TQ cells, and it's going to attempt to answer the query by accessing these cells. So the update and query algorithms are the update in queries are just nothing else but adaptive algorithms, so decision trees, okay, over this space. And what we care about is the trade-off between the update time and the query time. Does that make sense? That's going to be important for the talk. So again, I want to emphasize that the crucial feature of this model is that it's a non-uniform model of computation. So what you choose to do with those cells, or for example, the address of the next query, the fifth query, conditioned on the information you got from the first four, is a completely arbitrary function. You can choose to do whatever you want. That means that the performance here is completely independent of the set of operations you're using offline. I'm not charging you for any computation on the information you received. So it's a purely information theoretic question, right? The trade-offs. And indeed, lower bounds in this model, they seem to capture really any imaginable data structure. And that's the power of this model. So it's a purely information theoretic question between how many cells you need to access on an update versus the query time. Make sense? Unfortunately, this abstraction comes at a price, and it's probably not surprising that this model is very hard to prove lower bounds in because it's so powerful. And indeed, proving lower bounds on the maximum of the update or query time has been a very challenging enterprise. So in 1989, Fredman and Sachs invented the chronogram technique, which will come up soon. And they used it to prove the first log n over log n lower bound on either the query or update time of actually a big class of explicit data structure problems. And it wasn't until 2004 where Petrasco and Demain managed to shave off this log n factor. And actually, that was kind of a big deal. So you should understand how desperate the field is. So they proved the first explicit log n lower bound by the information transfer technique. And this was for the graph connectivity problem. So it was actually a decision problem. In 2012, like over a decade later, Larson made a near quadratic improvement on that, and where he proved a lower bound for dynamic 2D range counting, but for the weighted version. So the weighted version of range counting is where you have maybe even a fixed set of points in the two-dimensional grid, but each point has a weight assigned to it. So it has some W bit weight assigned to it, maybe some some weight, and a query again is a rectangle, and you need to report the sum of the weighted points inside this rectangle. Okay, so we'll come back to that, but this is the weighted version. So it's not exactly the classical range counting problem where you only need to report the number of points, but you need to report the sum of the weights.
Is the exactness important here?
So most of the data structures, lower bounds, have been proved for the exact problem. There are exceptions of, do you mean, so people studied, for example, approximate near neighbor queries and stuff like that. So you can talk about those things, but range counting, as far as I know, at least from the lower bound perspective, has been studied the exact case. So actually with watching you, we improved this to Casper's lower bound to an amortized case, even if you allow extremely high error. So you have to spend this much, these many probes at this much time on queries or updates, even if you want exponentially small, if you want to avoid exponentially small error. So, but the answer has to be exact. Yeah, it's just a randomized amortized version. Okay, so this was a real, breakthrough. Best paper in Fox, I believe, a few years back, but it had one substantial caveat. So the problem with Casper's lower bound was that it required huge outputs of queries. So it required each query to reveal, the sum of the weighted points reveals the weight modulus some number. That requires, let's say, 10 or 100 log n bits of output. And you might think that, okay, maybe this is just an artifact of the proof, but this fact was crucial. So somehow Larson used this fact to argue that the property that each answer to a query reveals a huge amount of information on the database was a crucial factor, and we'll see this in a second. And this is not just an artifact of the proof. So in fact, all previous attempts for proving super logarithmic cell probe lower bounds on dynamic problems, one way or another, required this assumption that the answer to the query will reveal a lot of information on the database. Okay, so if you normalize actually the lower bounds by the number of bits of the query, which is kind of the right scale, then we never actually cross the logarithmic barrier. So we're still stuck on the Petrashku domain frontier, okay? Because none of these lower bounds holds when the query output is small. Okay? So all this kind of journey raised a concrete milestone of, for proving higher lower bounds, which is to prove just a super logarithmic lower bound on any problem with a short output, with, in the extreme case, just a boolean, a decision problem. And I want to emphasize that this is not just, a toy problem. This is provably a prerequisite for proving, if we ever want to go beyond log squared n lower bounds, you must solve this challenge first. And the reason is simple, right? Because suppose we had a super log squared n lower bound for some arbitrary general, w-bit output problem, then you can use it to cook up a Boolean problem which has super logarithmic cell probe lower bound. Why? Because you just define a new problem based on this hard problem. We just output the ith bit of this general problem. It's not hard to see that log n executions of the Boolean problem can solve the big problem. So if you have a super log squared n for the general problem, you have a super logarithmic for one coordinate. Okay, this is a quick sketch. Does that make sense?
So why in fact couldn't Casper use it for, just use this reduction to prove log n squared, not super log n squared?
No, because you lose a factor of log n.
Yeah. So for,
Oh.
so if you have a Boolean lower bound, you can get a...
No, I mean if you have a lower bound for a large bit problem, like Casper's, if you have a lower bound, then you get the same lower bound for a Boolean problem divided by log n. So it gives you nothing. And in this work, we make progress on this barrier. So we prove a super logarithmic, a log to the 1.5 and lower bound for actually a large class of explicit dynamic Boolean problems. And I'm not going to elaborate on this in the favor of time, but the most notable problem we managed to prove a lower bound for is the two-dimensional, the 2D range counting problem over F2. So even if you only need to report the parity of the points, so you have unweighted points, so it's the classical range counting problem, but even if you need to point to output just the parity of points, you need to spend this much time. Actually, even if you have polylog, even log to the 10 update, you still must spend log to 1.5 query time. And I think the most appealing consequence of this lower bound is the first super logarithmic, so the first log to the 1.5n, lower bound for the classic unweighted range counting problem. So if the parity requires that time, of course the classic problem required. And that problem was still open. There was a gap between log n and log squared because Casper's lower bound only applied to the weighted problem where you have large weights. Does that make sense? And I remind you that it's not exactly tight because there's still like a square root log n factor, but it's not very far from the best upper bound. Okay, and supposed to be a picture of Mihai Petrascu here, but so Mihai left this as one of his favorite open problems in his, which was depicted in Mikkel Torup's obituary, and this basically this partially answers this problem. But I think the most interesting thing about this is really the new technique. Maybe not the result by its own. It's the new idea of how to think about data structures. So I want to try and give you a quick overview of Casper's lower bound, so we understand why the Boolean domain is such a bottleneck, right? So again, in Casper's setup, in the weighted 2D range counting problem, we have n points in the 2D two-dimensional grid. So we have n squared potential queries, right? N squared potential queries and n, let's say even fixed points. It doesn't really matter because they're weighted. So and the updates just specify a point and a weight, and the query is again a rectangle, and you need to report the sum of weights of points inside this rectangle. Okay, so the points have weights of, let's say, 10 log n bits, and you need to report the sum of points dominated. And I remind you, there's a log squared n upper bound, and Casper proved that for this weighted version, actually, this is essentially tight, up to polylog log n factors. Okay, so what is the high-level idea? I want to give you like a 10, 15-minute sketch of the high-level idea, and we'll see why it fails for the Boolean problem. So the idea is to say that if we have a too good to be true data structure that has pretty slow, not too fast update time, so polylog n, then after a random sequence of updates, so each update just chooses a random point and assigns it a random weight, a random query must probe in expectation a lot of cells from this update sequence, so roughly log squared n. All right? So the first step in this proof is to divide the sequence of updates, these online n updates, followed by a query. So we want to divide them into geometrically decreasing consecutive intervals where the size of each interval, the ith interval, is beta to the I for some beta, which is polylog n, and it is comparable to the update time in the word size. Remember, the word size is log n, update time is polylog, so beta is kind of some maybe log to the fourth n or something like that.
So this goes back to Friedman and Sachs.
Exactly. So it's a combination actually of the Friedman's, the epoch, the chronogram technique, and the cell sampling. So we'll see this in a second. All right. So if you ignore log n factors, the number of epochs is roughly log n, right? And you might ask yourself, what's the rationale behind it? What did we gain by this geometric decay? And what Friedman and Sachs proved, and this was a simple but very kind of novel idea, is that this geometric decay essentially reduces a dynamic problem on n updates to roughly log n, the number of epochs, independent static problems. In what sense? So first of all, we can indeed bundle up all the operations in each epoch and give you them at once. So you can pre-process everything that happened in one epoch. So this is similar to the static model. So the dynamic part of the feature of the problem is only on the epoch resolution, not inside every epoch. But why am I claiming that those problems are essentially independent? And they're independent in the following sense. So suppose you don't need to look at the bird at this point. Suppose you want to learn what happened in the ith epoch, let's say in the epoch number 12. By looking at the data structures, memory, right? That's the only way you can learn something. So you want to look at cells in the final memory state of the data structure, and you want to learn what happened in epoch number 12. I claim that the only cells that reveal information essentially about this epoch, about what happened in epoch number 12, are cells that were either read or written in this epoch itself. Why is that? Well, let's first look at the first 11 epochs. I claim that the cells probed during the first 11 epochs have nothing to do. They reveal no information about the 12th epoch. Why? That's easy. Because the updates are independent, right? The updates were chosen independently, and so you cannot predict the future, right? The first 11 epochs, whatever they do, they cannot reveal information of what happened in the 12th epoch.
It's important that these are random updates.
Right. Right. What about epochs what about epoch 13 or 14? We can no longer claim this, right? Because, and that's crucial, because the data structure is adaptive, in epoch number 15, it can overwrite or it can read a cell that was previously written in epoch number 12. So we cannot claim that future epochs don't reveal information. But the point is that there are so few of them, right, compared to the size of the 12th epoch. Does that make sense? That's important. That's the entire idea behind the chronogram. That's why we need to pay this geometric decay. So because of the geometric decay, the size of the 12th epoch is so much larger than all the cells that could ever be written in future epochs, because the number of updates in future epochs is negligible by the geometric decay, and each update can only ever touch T sub u times memory times W bits of information, right? That's why it's important to choose beta, the basis of the geometric decay, to be larger than the update time. Is that point, even if you ever learn anything from this talk, that let this be it. Is that point clear? So what I claim is that what does this mean? It means that we can essentially fix all remaining updates and only keep the ith interval live. We can do this for every epoch. It's enough to prove a lower bound on the number of queries, a number of probes that this random query makes to each epoch separately, because fixing the rest of the updates and everything that happened everywhere else is kind of irrelevant. Okay, so let's try to formalize this. Okay, so let AI denote the associated cells with the ith epoch. So these are exactly those cells whose last time that they were updated, written or read, was in the ith epoch. Okay, let this sink in. So this is going to be a crucial definition. So a cell number 113 is associated to epoch number 12 if the last time that its content has changed, or either read or written, was in epoch 12. So
you have written, but you keep saying either read or written.
Yeah, I think you can assume that it's also, it doesn't matter. Let's say read or just probed. Okay, so read or written. So it's a partition of the memory, right? It's a partition of the memory. And what we want to show in this language is that this last query that comes after this random sequence of epochs, of updates, needs to read roughly log n cells from each epoch separately. And I claim, is everyone convinced that would finish the proof? Because there are roughly log n epochs, each one needs to read log n cells, and we can argue separately by the chronogram method. So this would finish the proof. Questions about this? So is everyone happy with, you know, the argument that it's enough to keep only the ith epoch live for every I and fix the rest of the updates? They won't really affect the argument by the chronogram method. So we need to prove that this random query must probe a lot, like log n cells, from the associated cells with only the ith epoch, which is kept as a random variable. This is kept live. So what is the rationale behind this argument? So, oh, crap. You used to have Alice and Bob here, but OK. So the idea is, imagine Alice here with the entire update sequence. So she has everything, including UI, the live epoch. And Bob has everything except he's missing the ith update sequence. And the idea is to show that if we have a too good to be true data structure, if the data structure probes much fewer than log n cells from this epoch, from the epoch associated with the ith epoch.
On the cells associated.
Yeah, on the cells, sorry, the cells associated with the ith epoch. Then we can use this too good to be true data structure to give a too good to be true encoding of what happened, of the updates in this epoch. So this is what we're going to show. Is that clear? So we're going to compress the update sequence, which, as Avi said, is completely random independent, using less than the entropy, less than the size of this epoch, number of bits, which is a contradiction, information theoretic contradiction. So how is Alice going to do this? Of course, she can just send the live updates. That won't gain us anything, right? So she's going to do something more clever. What she's going to do is, so I'm describing the encoding function, the encoder. So Alice is going to sample.
Just to make sure, a sanity check, this should not work if it was one-dimensional.
It would give you just it would give you a right. This wouldn't
this
not work.
This argument cannot work.
And we'll see.
There will be a lower bound for
But it would give you it would recover the Fredman-Sachs lower bound. So what I'm saying is that you can use cell sampling to recover Fredman-Sachs, I believe.
Yeah.
Okay. And actually, that's a good point. There are many ways.
Just a constant lower bound.
Exactly. But I'm saying if all you want is not a log n lower bound from each epoch, but just constant, which is what, then there are there's a simpler argument. So what is Alice going to do? She wants to encode the ith epoch. So what she's going to do, instead of just naively sending it, she's going to first generate the memory state of the data structure. She has all the information to do that, right? She has the entire update sequence. And from now on, so the light green cells are going to be precisely the associated cells. So these are the cells that were probed for the last time in this ith epoch. Remember, it's a partition of the cell. So what Alice is going to do, first she's going to send all the updated contents of all the cells, all the white cells that were updated in future epochs. Okay, that's going to be relatively cheap. Why? Because there are few of them, right? There are just few updates. And notice that this is important because cells can get overwritten. So it's important that Alice sends all the updated content of all the future cells. Number of future cells that can be ever probed, because the update time is slow, it can never. It's negligible compared to this. But what is she going to do for the ith epoch? Again, she can't afford to send all the light green cells, the associated. So instead, she's going to subsample independently with probability p, which is kind of 1 over polylog n, every light green cell, every associated cell, and she's going to send it to Bob. Only those associated cells, or only this subsample of cells. I'm not asking you to understand why this works, but is it well defined? Does everyone? So that's it. That's the encoding. Alice just sends Bob all the updated, up-to-date memory content of all future cells, and for the ith epoch, she doesn't send everything. She just sends, some random subsample of those light green cells, which we henceforth color in dark green. Okay, so there are 3 kinds of cells. white, which was probed in any other epoch, light green, which is relevant to the ith epoch, so it was probed in the ith epoch, and dark green, which is a light green that was actually sampled by Alice and sent. That clear? Okay, let's analyze. So what is Bob going to do? How is Bob going to use this to decode? Well, Bob has some induced posterior memory state sent by, induced by Alice's message, right? It may or may not be wrong. Of course, it's not correct, right? Because Bob is missing a lot of unsampled cells, right, in the memory. So there are a lot of cells whose content is not updated. In cell number 113, it is written 7, but it should have written, jump to cell 47, right? So a lot of cells are corrupted, actually. But, Bob is going to do his best. He's just going to, try to answer as many queries as he can with his respective memory state. He's going to hope for the best. So, and what is Bob's hope here? So Bob is going to hope that every query that he answers correctly gives him $1, give him one independent bit of information on the memory, on the updates, on the sequence of updates. Okay, we'll see that it's not a non-trivial property of the data structure problem, but this is the hope. Okay, so let's focus on a fixed query, Q. What is the probability that Bob can answer a fixed query? There's a fixed query Q, right? There are n squared of these, right? N squared queries. What is the probability that Bob can answer this query? Well, I claim it's just the probability that the set of cells, we call it SQ, that the data structure probes, contains no unsampled light green cells, right? Because this is a bad situation, right? Because Bob thinks he has the right content. He thinks it's white, right? Alice didn't subsample this. But the content here is actually corrupted. Does that make sense? So it's the probability that no light green cell is being probed in this. But the query time, we assumed it's small, right? We assumed that the data structure only probes much fewer than log n light green cells. And each cell was independently subsampled with probability p. So what's the probability that all of the cells were actually dark green, that they were sampled? Just p to the query time, right? Just the probability that all the light green cells are actually dark green. Is that argument clear? So if you set remember, p was like 1 over polylog n, 1 over log to the constant n. And if you set the parameters correctly, this is going to be much larger than 1 over n chance, or 1 over n probability, or fraction of answering. And there are n squared queries. Remember, there are n squared queries, and Bob can answer in expectation at least n of them, let's say, or even more. So now Bob can hope that, if it were the case, and it's a big if, it's not trivial at all, if it were the case that any query, any range counting query gives Bob one full bit of information, independent bit of information on the database, then answering more than n queries would recover, or maybe square root n queries, would recover all the updates in the ith epoch. Because the ith epoch, think of the number of updates in the ith epoch as being some square root n or something like that. Unfortunately, range counting, it's a good exercise. It lacks this property. It doesn't have this property that every query gives you an independent bit of information. It's a good exercise to see why. So you need to work pretty hard to make this problem, to convert it into a problem which is sort of n-wise independent. What do I mean by n-wise independent? If you look at the answer vector, it's an n squared coordinate vector. If you look at any n locations, it's a random variable over the update sequence, right, the UI. If you look at any n locations, any n answers, you want them to be independent. And this is not true for range counting, but if you consider, if you take if you consider tuples of queries, if you just take direct products of over tuples, then this works. And this was done in some previous works, but it takes like 2-3 pages, but it works. Okay.
Is there another problem, or is there a different problem not mentioned?
Sorry?
Is there a different problem you could have started with where you wouldn't have to do
Yeah, great question. Yes. So polynomial evaluation was the original problem. So let me just say one word about it. Polynomial evaluation is the data structure problem where you have some underlying finite field, a degree d polynomial. Updates are just changes to the coefficients of this degree d polynomial. And queries are points in the field. You need to return the evaluation of the polynomial. So as Tony suggests, this problem has precisely this clean and nice, elegant d-wise independence property in the sense that any d queries, any d evaluations of the polynomial that you answer correctly, that Bob will answer correctly, he will fully recover the polynomial. It doesn't matter which d. Okay? So actually Casper started with this lower bound, and then for range counting, which is more kind of natural, he had to work much harder. So no, because of the problem that we'll see in a second. But in our paper, we prove the same log to the 1.5 for the parity version of polynomials. Yeah, and it's actually, it saves you quite a bit of work. But the answer is that his lower bound will not work for a reason that we'll see in a second. Okay, so I claim that this will essentially finish the proof, because if you believe that the problem does have this n-wise independent property, so Bob only needs to collect enough points of queries, doesn't matter really which, then he essentially learns too much. He recovers essentially the entire update sequence. But how much did Alice pay? I claim that Alice's message is much shorter than the entropy, than the size of the input. Why? It's just, what is the cost of Alice's message? Sending the future contents is negligible, right? Now, it's just essentially proportional to the number of cells that were dark green, that were subsampled. Right? How many of those are there? Well, it's the size of the light green cells divided by, multiplied by the probability. This is the expected number. And, if W is log n, this is poly log n. And the update time, right? The size of this set can be at most the size of the update sequence times how many cells are updated in each update. This is much smaller. It's like UI over poly log n. Okay, so it's much smaller than the entropy. Is that point clear? So Alice managed to compress the update sequence to encode it using this too good to be true data structure. Right? And note that we used crucially the fact that the query time is fast. Right? Is logarithmic, because this induces a large fraction of correct queries. Okay, so we said range counting lacks this property, but otherwise the proof is done. There's one problem though. Where did I use the large weights? I never actually used this argument might as well work for the boolean problem, right? So the point is that it's true that there's going to be a large set of queries that Bob can answer. Right? So this is the n squared set of queries. Right? It's true that there is going to be a very large set, T, of, more than even n queries, which is all that Bob needs. But Bob doesn't know to detect this set. Why is that? Because just look at the picture. So Bob tries to answer this query, right? He does his best. He starts reading the memory contents. He doesn't know that this cell is light green, right? He thinks it's white. He has no way to verify it. Does that make sense? It's a subtle but important point. He has no way to verify whether this point is this memory cell is actually light green or white. So he doesn't know the false positives here, right? And Alice cannot tell him that because Alice doesn't know the query. Only Bob has the query, kind of. Okay, or in this language, when Bob enumerates over all the queries, Alice cannot afford to tell him everything. So is that point clear? So Bob doesn't know to identify this event. And this means that the fact that there's a large set of good queries is completely worthless for him, because he doesn't know to detect this. If he knew how to detect, he would just ignore the queries which are not in this set and only use the good ones. He knows there are sufficiently many, but he doesn't know how to detect them. So how does Casper resolve this problem? Well, Casper says, okay, fine, but let Alice just send Bob this set, T. It's a subset of n squared points, right? Some subset. But how much does this then surely Bob can do everything, right? He knows what. But this requires sending roughly log n bits, the name of the good queries, the name of the elements in this set, T. That requires roughly, log of the number of queries. You just need to spend. So you see, if such a compression argument is ever going to work, it better be the case that the answer you learn, that Bob learns from a query, is larger than the number of bits required to specify this query. Otherwise, a compression argument can never work, right? Alice is trying to encode a query by more than the content of this query. This is exactly the reason that Casper needs large weights. Is that point clear? Clear to everyone? So the reason why you need large weights is you need the information to a query to reveal more than log of the number of queries. Log of n squared is like 2 log n. You need more than, let's say, 3 or 10 log n bits in order to ever hope for such an encoding argument to go through. Okay? And implicitly, you might think this is just an artificial proof, but this was essentially the bottleneck in all the proofs. So, Mihai solved it with some Bloom filter argument, and we solved it with some other non-deterministic guesses, but everything requires large weights because you cannot identify the good event. Okay? So what is our approach to the problem? We take a kind of a similar approach. We define the epoch communication game between Alice and Bob, which is kind of similar. So we still have the same chronogram, division to epochs, and we give Alice the entire update sequence, and Bob has everything except the ith epoch. Okay, and okay, so it's the same picture. Only the ith epoch is live, and in the induced communication game on the ith epoch, again, the goal is to just answer. Okay, so and Bob gets the query, as well. So Alice has all the updates, Bob has the query, so neither of them can solve the problem on his own, right? Alice doesn't know the query, Bob doesn't know the ith epoch. And the goal is to solve this problem, to answer the data structure query on this update, using a one-way protocol in which Alice speaks first. So it's essentially the encoding argument, but I guess in a slightly different with some side information, whatever. Okay? So again, of course, the trivial protocol is to just send Bob the missing updates, right? Remember, Bob cannot speak, so the trivial protocol for this task is this. But actually, we are fine with even a tiny advantage over random guessing. By the way, this data structure, this communication problem is defined for any Boolean data structure problem. So any Boolean data structure problem P, our main result is this kind of weak simulation theorem that says that if you have a too good to be true data structure for this arbitrary Boolean dynamic problem on n updates, then that has update time tu and query time tq, then you can use this too good to be true dynamic data structure to design a protocol for this epoch communication game on the ith epoch, which has kind of non-trivial communication. So again, just ignore this. Think of this as polylog, right? W is log n, tu is some polylog. So this is like ui over polylog. So we get a polylogarithmic savings on the communication. And it lets Bob answer the query with a tiny but non-trivial advantage over random guessing. So he can always guess the answer. It's a Boolean problem, right? Probability half. But he can actually get, if you think of tu as polylog and ignore this term, then it gets him exponential and minus the query time over square root the number of epochs Square root, yeah, the number of epochs, roughly, advantage. So I'm not asking you again to understand, just does that parse? That's the main result. Now I'm going to try in 10 minutes convince you why is it enough to prove our log to the 1.5n lower bound. I'll try to sketch the proof because this is where actually the paper begins. So just try to sketch this fast.
So is it one of these lower bounds where either TQ is bigger than log n to the 1.5 or TU is actually bigger than n to the epsilon?
No, it doesn't fit. So I think that
I don't see TU.
I think the point, kind of the chronogram method, any problem in which you're using the chronogram method is insensitive to polylogarithmic changes in the update time, because then the number of epochs is log base the update time of n. So if the update time is log, but if it does that make sense? Remember
there it's not the 1.5 is not about the update time. It's really about
exactly, exactly, exactly. So remember the number of epochs is log base beta. Beta was roughly the update time of the number of updates. If this is log to the 10n or log to the 100n, doesn't really matter. It's just poly log n factors, right?
So that means your lower bound still applies even if you make them.
This is exactly what Avi says, right? That even if your update time is log to the 1000n, you still need to spend log to the 1.5. But if you set the update time to be n to the epsilon, you'll get only a constant number of updates. Okay. Yeah.
In the statement, this is what all is random? Is it
It's
Q and the
sorry.
It's not for every epoch, but for a typical.
It's for the typical or the cheapest epoch in which you're. So if your total query time is TQ, and there are n epochs, there must be an epoch in which you're probing TQ over the number of epoch cells, right?
for the Qs, is it also randomized over
Yeah, it's for a random query. It's for a random.
Everything's random.
Yeah. Okay. So let me first convince you in 3 minutes. Why is it enough? The first caveat, the first thing you might ask yourself, it's very different than what Casper. It's much stronger than what Casper was hoping for. We're attempting to decode the entire update sequence. This is all the way all the proofs work. Not by answering, collecting n bits of information, but by answering only a tiny better than half of the queries, only a tiny fraction better than the full n squared queries. Why is that enough?
Just entropy counting.
Okay, maybe what I was about to say is just the answer is list decoding properties of random codes. So so here's the 2-minute explanation. I think for this audience it shouldn't be hard.
But it's just to understand, this will hold for any data structure problem. The proof now is
Any data structure problem. This theorem holds for any data structure. No. Okay. The argument I'm going to say now, okay, let me say it and then I'll say what it applies. So why is it enough to prove our log to 1 to 1.5 and lower bound, even if we get such tiny advantage? So the reason is, so think of a data structure. It will be useful we can think of a data structure as mapping the random update sequence as a code. It's simply a code that maps the code word, which is the original message, which is the update sequence, to a truth table of n squared answers. So it's a boolean problem. So we have just n squared coordinate vector, right? And remember our weak simulation theorem gives us some tiny advantage. Forget what's written here for now. It's just some epsilon advantage. What does that mean in terms of a code? Now I'm going to say something that is specialized to the problem. If our problem, dynamic problem, had this looked like a random code word, in n squared space. Of course, it cannot. The entropy of the code word is only n, roughly. But if it looked pseudo-random, if it was a random code, so if a random update sequence was mapped to a random point in n squared space, then what is this theorem telling us? It tells us that if this is the true n squared vector of answers to all the range counting queries, we can recover by this weak simulation theorem, by the the too good to be true data structure, a point which is almost as far as possible, almost distance half, but actually not quite, a little bit better than half. So it's in distance half minus epsilon of the true code word. And we know that, for a random code, we cannot have more than like 1 over epsilon squared potential candidates in this shubangis, right? So is that clear? So what I'm saying is that for a random, if your problem looks like a random code, the truth table of the answers, then decoding the exact thing or decoding it up to only recovering the true values only of a tiny fraction, let's say a polynomial small fraction beyond half, is almost the same, because if, in the ball of radius half minus 1 over n to the 10, there are only like n to the 100, some polynomial number of potential black points that could be arising from this original message. So morally speaking, Alice could just send the index of this 1 of the n to the 100. That only costs log n bits. So I want you to, this is an important point for the lower bound. Instead of answering a lot of queries, it's actually for random looking problems, which is kind of the n-wise independence property I was alluding to. So for polynomial evaluation, it will work perfectly. It will work exactly. Recovering the true answer vector, or recovering a random query, only with a tiny advantage, is essentially equivalent to recovering the entire point, because there are so few candidates, because the list decoding radius of a random code is just half, basically. Does that make sense? So what does that mean combined with this theorem? Well, Alice sent a short message in the simulation theorem, so she better not be able to recover this fraction of queries, like 1 over n to the 10, right? Because otherwise it's a contradiction. Alice sent much fewer than number of epochs bit, than the number of updates bit. So this advantage by the weak simulation theorem better be smaller than 1 over n to the 10. Is that clear? Because if it weren't, then Alice could essentially send another extra log n bits telling Bob which is the index of the list corresponding to the true vector, and this will be an information theoretic contradiction. She would manage to compress the entire update sequence. And you rearrange and you get exactly log to the 1.5. It's exactly where it comes from. Make sense?
So where the log n to the half come from? In the advantage?
Yeah, okay, now I was okay, so I want to, do I have 5 minutes? Or, okay, so I want, if you believe this theorem, wow, I don't know what happened to the slide. If you believe this theorem, this is the main result, then are you convinced that a log to the 1.5 and bound follows? And again, this random looking property, this n-wise independence, it's not a trivial property. For polynomial evaluation, it's much easier. For range counting, you actually need to work a little harder. But this is the idea. What I'm trying to say is that if you look at the paper, don't bother reading the extra 5. I mean, this is not where the interesting action happens. This is where the interesting action happens.
So for if we only wanted to do it for polynomial evaluation, we could use straight out of the list decoding.
Not exactly, because okay.
But
I believe that the answer is yes. Somehow Casper insisted on doing it using a high. Basically, how do you encode this? And what independence, you look at higher moments of the queries. But I believe that if you did it, you could do it this way.
So you are not using directly the list decoding properties of Wigmiller.
Right. We're using it. Right. We're using it as intuition. I believe that if you try to do it, you would succeed. That's what I'm saying. That's all I'm saying. But yeah. I'm saying I feel the list decoding argument is much more intuitive, and I believe it can be made to work. We didn't spend time on trying to simplify the proof. That's all I'm saying.
Omri, you've been hiding polylogs from us? Like
Polylog-logs.
Polylog-logs. Sorry,
Yeah.
Okay.
So I want you to ignore this term because it's not good looking, right?
The
So
lower
just
bound that you showed us is false, right? Or you don't have that. There's like a log.
there's a log.
or something.
There's a log.
Okay.
There's a log factor. So I claim that now I'm going to state, this theorem applies to any data structure, any Boolean data structure problem, regardless of this n-wise independence. The list decoding thing applies only to special data structure, but this applies to any Boolean dynamic problem. So let me try to give a quick sketch of what's going on here. So remember, Bob is missing the ith epoch, and Alice wants to send a small message, right? So what would you do given Casper's proof? What is the natural strategy for this problem?
Sample less.
Or let's start with sampling exactly what he does. So first of all, let's focus. So Tony asked this, I think. What is the ith epoch that we want to focus on? As Tony and Avi said, there's the total number of cell probes. The total query time is TQ. There are log n epochs. There must be an epoch where the data structure reads at most TQ over log n cells. Make sense? Because the associated cells are a partition of the memory state. Let's focus on this I, okay? And forget all the rest. So the query time here is relatively small, right? It's TQ over log n, the typical query time. Make sense? So remember this number. This is the total number of probes for the light green cells, right? From the light green cells. So what is the natural approach given Casper's thing? Well, let's do the same thing. Let's have Alice subsample each light green cells with probability p, which is 1 over polylog n. She just sends it to Bob. We know it's cheap. We know the message size is fine. It's much less than the total communication cost is much less than the entropy of the ith update sequence. And let's denote by WQ the event of success, the probability that the data structure probes only dark green cells. So far, so good. By the previous argument, right? Remember, the data structure only probes TQ over log n light green cells by definition of this epoch, right? So the probability that all of them are sampled are exponential in minus TQ actually over log n, not over square root log n. Okay, so let's denote this advantage by epsilon. Does everyone agree that if this event occur where, Q is this random query, if all the cells that the data structure reading are dark green, so Bob has the perfect, either dark green or white, right? White cells were always fine. The only occasion where we're not fine is if the data structure probes a light green, which is not dark green, because then Bob has a corrupted content. Everyone happy with the claim that if all of them are dark green, he has perfectly the answer. But again, Bob cannot detect this event, right? Does everyone see this? Because if Bob takes his, the message that Alice sent him, he has some posterior memory state, may or may not be true, simulates the query algorithm. If Bob probes a light green cells, he thinks it's white. He thinks he has the right content, 212. But it's light green, but it was not sampled. So Bob can never know this. He has a false positive probability that, so I claim that this is completely useless. And Alice cannot tell him whether he's right or not because she doesn't know the query. Does everyone see? It's precisely the same problem that Casper. And in fact, if this were true, if there was a cheap way of verifying, of detecting this event, that all the light green cells are dark green, not only would this finish the proof immediately of this simulation, it would prove the advantage would be exponential minus TQ over log n, not over square root log n, which is what I'm showing you, which would close the problem. It would settle the range counting problem. And would prove our simulation theorem in two lines. But there's no way of detecting this event. So we're back to square one, right? We're back to the bottleneck that faced by all of these, 5-6 papers, that they never managed to overcome the problem of verifying this good event. So what can we do? You think about it and you say, right, so this is the bad event, right? Because you sampled a light green cell. So actually, not only, I just want to convince you, and we did, okay, let me say this in a second. So again, certifying the event W is expensive, And you ask yourself, okay, so what else can Bob do? He just needs, remember, all we're fighting for is a tiny advantage. He just needs to send a few more bits. Alice needs to send maybe some few other bits just to move the bias away from half. That's all we're asking for. But unfortunately, and it's not hard to see that, no matter what Alice, so this should be clear, no matter what Alice says, Bob has one unique optimal, answer strategy. What is it? It's just maximum likelihood, right? Bob has some posterior distribution given Alice's message, whatever Alice's message is. Outputting the more likely bit 0 or 1 is always the best strategy, right? So I want to emphasize that for the previous slide, if Alice doesn't send anything further except these subsampled cells, we do have actual concrete examples where you're basically the mutual information, if Bob uses this maximum likelihood, the mutual information of this Alice's message, right, which could be true with some tiny probability, but Bob cannot detect it, with the lack of the ability to certify the event, this could be 0, precisely 0, not almost, like exactly 0. So we need some new idea. We need something else that Alice, so you think, okay, so this as is cannot work, cell sampling, but maybe there's some cheap further message that Alice can send that will drive away the bias from 0, okay? And that's the main question we asked ourselves. So our hope is that Alice, beyond the cell sample, can provide a little information that will drive away the bias from half. All we're fighting for is a tiny advantage, right? So here's the main lemma that we state and prove. It's actually okay, so let me state it. This is kind of the heart of the paper, and then we'll see if we have time to talk about the proof. The proof is actually 5 minutes. It took us a long time to find it, but it's very short. So here's the question. So if you slept during the lecture, this is the time to wake up. It's a completely fresh question, so in information theory. So suppose you have a k-variate random variable, z, which is jointly distributed with some random variable b, which is, let's say, binary. Okay, so you have a pair of random variable, a vector, a k vector, let's say k-binary vector, random variable, and a random variable b.
We shouldn't think of b as a function of.
Yeah, so actually b will, okay, I was planning to say this in a minute. Z is going to be the memory contents of Bob's path in the decision tree in the query algorithm. It's going to be the contents that he probed, which may or may not be correct, depending whether, actually it's very unlikely to be correct because Alice most likely didn't sample all the correct cells. With some small probability, it's the correct path. And B is just the posterior answer vector conditioned on Alice's message, whether it's the answer to the range counting problem is 0 or 1.
It's a function.
So it's a function. But forget this. Let me state a clean information theoretic problem. You have a jointly distributed pair of random variable. One is a k-variate vector z, and jointly distributed with some random bit, which is marginally random, okay, marginally bias half. And I tell you nothing about the correlation between these two, except one fact. I tell you that there is some assignment, there is some singleton assignment. There's one assignment to the k-bit string that conditioned on this assignment, b is totally predictable, so it's a function of z. Okay? What do we know else about the correlation? Absolutely nothing. So it's a pair of, the correlation between these two can be arbitrarily complicated. I tell you nothing except this. This is the only fact that captures the correlation between the two. And the question is, what is the smallest number of coordinates in z? Let's say, what is the smallest subset of k coordinates that we can, that conditioned on them gives you an average advantage of it. The bit b was originally one bit of information, was an unbiased coin. I want to condition a smaller subset than k such that it drives away the bias. It's slightly unbiased. Does the question make sense? It's a completely clean question, whatever, forget what you saw. So you think about this question for a second, you realize without this condition, it's definitely too good to be true. Why? Because B could just be the parity of these things. If you reveal anything less than k coordinates, you get nothing. Not almost nothing, nothing exactly. You get zero information. Does that make sense? So this condition must somehow be crucial for anything to work. And really the heart of the paper is that actually conditioning on square root k, roughly square root k, or square root k log 1 over epsilon coordinates, suffices to get not a constant advantage, but some exponential and square root k advantage. So it's the same expression here.
Epsilon we think of as like a constant here? Is that
No, no. Epsilon, remember, is the success probability of the algorithm. It's the probability that Alice samples all the dark green cells. So epsilon is p to the, to the query time,
like 1 over n?
which is 1 over polylog log n. It's just this number, okay, where p is 1 over polylog n.
So, only because there's the machine learning seminar and some people are
Yeah.
going to it and
Okay.
they start
Okay.
serving food. Why don't you take a minute or two to just tell us
Okay.
what goes
Okay.
into the
2 minutes.
even without
2 minutes.
the
No, actually, you can prove it in 2 minutes. Let me just say that you might think, oh, this theorem is tight. So there are functions, there are distributions where if you condition on little o of these number of coordinates, you get exactly zero advantage. Not almost, exactly. And actually, so I showed Scherstoff the proof, and he found immediately an elegant way to found a, to show that it's tight. And actually, it's a very nice argument using dual polynomials. But yeah, oh,
I mean, the square
you ruined the punch. But okay, it's written in the abstract. So let me just tell you how do you prove this. So I just want to make sure that you understand the lemma is tight in the strongest kind of possible sense. So here's the formulation we actually prove, and I can show you why it's equivalent. It's a functional analytic or an algebraic essentially equivalent. So we show that if you have a function, let's say, suppose on a k-bit strings, in our case the alphabet will be the word size, but it's a k-bit string, it's the same. And you know that its L1 norm is at most 1, so it has bounded L1 norm. And it has some peak, it has some L infinity, and you can translate it, right? F in our language will be the posterior bias conditioned on Alice's message that Bob had. And what is going to be the peak? It's going to be the right assignment, the event, the assignment of the conditioned on the good event, conditioned on which Bob can completely predict the function. And we know that it occurs with probability epsilon. Okay? Okay, I'm forgetting the data structure problem now. Just the claim is that there is a small set of coordinates such that if you condition and then an assignment to these coordinates, in the binary case, it's the all ones assignment, but it could be general, such that the average, not the average of the absolute values, the actual average is bounded away from 0. And you can see that without this condition of yeah, and you can see that without this condition, it's completely hopeless because things can cancel out, right? This is the bias, so it can be positive or negative. So things can cancel out and be identically 0. And again, we have counterexamples showing that without this condition, it can be 0. So 1 minute proof of the claim. That's
excellent.
1 minute proof. I can't believe this. So there should have been a Chebyshev polynomial. 2 minutes.
Actually, yeah, no, I think that this was 2 minutes. So since I promised something.
Yeah. Okay. So. Okay, what you do is you take your function f and you multiply it by a Chebyshev polynomial. What happens in this case? The peak is preserved because Chebyshev has a peak at 1. All the rest of the values are dampened a lot. So there must be one coordinate there must be one monomial out of these small monomials because it has a small degree that contributes a lot. This small subset is exactly the indicator of this monomial. That's it. That's the proof. So that's it. So I'll end here. Yeah.
All right, thanks a lot.
Yeah. Please.